Hello everyone, welcome to this lecture 25 of the NPTEL course on Riemannian geometry. So in the previous lecture I introduced this notion of Ricci curvature. So recall that the Ricci curvature was a map that took in two vector fields and it spits out a smooth function. It is defined in the following way. So Ricci of x comma y evaluated at a point P is simply the trace of the operator V going to R of V comma xp acting on yp, right. So here V is some tangent vector at P. So then we proved last time that Ricci so defined forms a 0 to tensor, and in fact it forms a symmetric tensor. Now one can choose a local frame which I denote by as usual by E1 to En for the tangent bundle on some open set U, and suppose epsilon 1 up to epsilon n is the dual frame. Then we as a tensor we can write the Ricci curvature as simply Rij times epsilon I tensored with epsilon j, where Rij evaluated at P is a symmetric, I mean the collection of all these Rij's as I and j vary is a symmetric n cross n matrix for every point P in U, right. So today the first thing I want to do is I want to talk about some other properties of the Ricci curvature, and then I want to define a further trace of the Ricci curvature called the scalar curvature, and then I will sort of so now at the end of that we would have had defined various curvature operators. We had the Riemann curvature endomorphism, we had the Riemann curvature tensor, now we have the Ricci curvature, then the scalar curvature, in between we also had the sectional curvature. So towards the end of the lecture I would like to comment on how complicated really these various avatars of the curvature tensor are relative to each other, right. So I will do that towards the end, right. So to begin with I want to state and prove the following proposition. So as above, let E1 up to En be a local frame and epsilon I up to epsilon n be a dual frame for the cotangent space. Okay, then we have the following. Rjk, which were the components of the Ricci tensor, can be obtained by the from the components of the curvature endomorphism by summing up the first and the last index, right, or in terms of the Riemann curvature tensor this is the same as GIL Rijkl, okay. And then by using the symmetries of the tensor this is also the same as G upper IL Rjilk, okay. Secondly, suppose my local frame is actually orthonormal, okay, then in fact the Ricci tensor evaluated on x comma y is simply given by summation I going from 1 to n Rm of Ei x y Ei, okay. And thirdly, suppose xp is a unit vector, so its norm is 1, and let us say I have chosen my local orthonormal frame such that the final component is xp. One can always do that by just repeating the Gram-Schmidt process that I had described in order to construct an orthonormal frame in the first place. So one can always specify the first or the last vector that one wants. Then if you look at the quadratic form associated to the Ricci tensor. So by definition this is simply Ricci of xp comma xp, then that can be computed in terms of the sectional curvature, that is just the summation of the sectional curvatures of these planes pi I going from 1 to n minus 1, where pi I is simply the plane spanned by EI and En. Remember En was just xp, right, where I goes from 1 all the way up to n minus 1. Okay, so this is a useful proposition if you want to calculate the Ricci curvature, and it also tells you how really explicitly how the Ricci curvature depends on the sectional curvature and on the curvature tensor. Okay, let me, before I begin the proof, let me maybe just remark that because Ricci is a symmetric tensor, we have the polarization identity. So by polarization, Ricci of xy is actually determined by the quadratic form using this formula. This whole thing divided by 2, right, and by the third part of the proposition, the quadratic form can be evaluated in terms of the sectional curvature. So in particular the Ricci curvature is completely, I mean, can be completely determined by the sectional curvature, which is not surprising excuse me, so which is not surprising because in the previous lecture we also proved a theorem that said that the sectional curvature completely determines the curvature tensor, right. So this is not completely surprising at all. Okay, so let us prove the proposition now. So by definition, what is RJK? That is simply the Ricci tensor evaluated on EJ EK, which by definition is simply the trace of the endomorphism where V is taken to R of V comma EJ acting on EK. Okay. But what is the matrix of this endomorphism? So call this endomorphism A. The matrix of the endomorphism is simply given by let's call it AIL, where what is AIL? Well, you apply R to EI comma EJ comma EK, this should be equal to AIL times EL. By definition, I mean, that is how you write down the matrix of a linear transformation, right. But by definition this is also RIJK upper L times EL. So now just equate this with this and you see that the matrix of the linear transformation AIL is simply given by RIJKL, and so then the trace of this linear transformation, which is the Ricci curvature of EJ comma EK, so this is the trace of AIL. So that is simply the summation of the diagonal terms, which by our observation is simply this. Okay, so that proves the first part of the proposition. For the second part, suppose now that E1 up to En is an orthonormal frame. Okay, so then by the first part, what is RJK? That is simply GIL RIJKL, but because I am working with an orthonormal frame, note that Gij is the inner product of EI EJ, that is going to be delta Ij, which means that the matrix representing the metric, so the components Gij, that matrix is precisely the identity matrix. So the inverse will also be the identity matrix. So this will just be delta IL Ri JKL, which is simply Rijki, right, where you sum over, of course, as usual, the repeated index. But by definition this is simply this. Okay, so now given any arbitrary vector fields, so given arbitrary vector fields, suppose in this frame this is precisely this and y can be written as yk ek, then what is the Ricci curvature of x comma y? That is precisely r jk xj yk by what we just observed. Rjk is simply Rm of Ei comma Ej comma Ek comma Ei, and this whole thing multiplied by xj yk, where you also now sum over j and k, but that is the same thing as summation I going from 1 to n by multilinearity of the curvature tensor. This is the same as this. Where again you sum over j and k, so that is just going to give you Rm of Ei x comma y comma Ei. Okay, so that proves the second part. For the third part, note that we are now assuming that again that this is an orthonormal frame, which in particular implies that if you take Ei wedge Ej, the norm squared of that is 1, right. Okay, so now by the second part, Ricci of x comma x is simply I going from 1 to n Rm of Ei x comma Ei, but notice that this is precisely the sectional curvature of the plane spanned by Ei and x. Okay, so and recall that I am calling this the plane pi I. So this is precisely summation I going from 1 to n, right. So I should so this is precisely the sectional curvature of this if I is not equal to n, and if I is equal to n, then this term is precisely En because x is En by the skew symmetry of the curvature tensor, this term is 0. So the upshot is that Ricci of x is the summation I going from 1 to n minus 1 of the sectional curvatures of this plane pi I, which is exactly what I claimed. Okay, so this proves part 3 of the proposition. All right, so the next thing I want to do is take a further trace and define the scalar curvature. So the scalar curvature is defined as S is simply the trace of the Ricci curvature, okay, or in other words we have the following proposition: that let E1 to En be a local frame with, as usual, Gij being given by Ei Ej, then the scalar curvature is precisely G upper Ij times Rij, and you sum over I and j. Okay, so if for instance this is actually an orthonormal frame, then the scalar curvature is precisely just Ricci of Ei comma Ei, where I goes from 1 to n, right. So if you take the matrix corresponding to if you take the matrix for the Ricci tensor corresponding to this basis, then essentially you are just summing up the diagonal terms, right. So that is the scalar curvature. So the thing to note is that Ricci is a tensor, whereas scalar curvature is just a smooth function, which means that at every point the scalar curvature is just a number, right. So obviously it's much easier to handle than the Ricci curvature or the curvature tensor. On the other hand, because you are taking these various traces, the Ricci curvature and the scalar curvature contain less information, strictly less information, mostly strictly less information than the curvature tensor. Okay. All right. So how do you sort of quantify this statement that I made that the Ricci and the scalar curvature contain less information than the curvature tensor? So one very naive way of trying to quantify this is to look at the number of free parameters that determine the curvature tensor and the Ricci and the scalar curvatures, right. So really I want to end this lecture with some remarks. How complicated is the curvature tensor in comparison to the Ricci curvature tensor? So let us just everything is point wise because all of these are tensors, so one can just evaluate them at a point. So let us fix a point P and let us consider the following numbers. So D of Rm, this is number of independent components, okay. So note that a priori, since Rm is a 0,4 tensor, a priori it has n to the 4 components, right. But on the other hand, the curvature tensor also has plenty of symmetries. It has skew symmetry in these two indices, it has skew symmetry in these two indices, and then you can also flip the first pair with the second pair, and you have some sort of symmetry there, plus there is also the algebraic Bianchi, right. So clearly not all of these choices are completely independent, right. Okay, so it turns out if you do this counting, this is a good combinatorics exercise, then it turns out that this number is precisely n squared times n squared minus 1 divided by 12, okay, which of course as you can see is strictly less than n to the 4, okay, is actually much less than n to the 4. Okay. Similarly, I look at D of Ricci, so this is the number of independent components of the Ricci tensor. So the Ricci tensor is symmetric, so the space of symmetric matrices, I mean the space of all n cross n matrices is of dimension n squared, but the space of symmetric matrices is basically of dimension n times n plus 1 by 2, right, because the idea is that you first can pick the first column arbitrarily, but then you basically can pick a further n minus 1 components arbitrarily and so on. Then you get this diagonal and then you just reflect this matrix about the diagonal, right. So clearly D of Ricci is n times n plus 1 by 2, and similarly what is D of the scalar curvature, that is obviously 1 because the scalar curvature is a function, right. Okay, so so let us look at the lower dimensional case. So let us look at n equals 2 first. So when n is 2, what is D of Rm? So that is 2 squared times 2 squared minus 1 by 12. So that is 4 into 3 by 12, right. So so in fact the curvature tensor has only one sort of independent component, and in fact one can just take the sectional curvature of the entire tangent space, that is just one number, that is usually called the Gauss curvature. So this is called the Gauss curvature, and this completely determines the curvature tensor. In fact in dimension 2 one can just check that Rm is simply given by k times, so it is simply given by GIL GJK minus GIK GJL, okay. And then in this case the Ricci curvature can be computed as just k times Gij, and the scalar curvature can be computed as 2 times k, okay. So basically this one number, the Gauss curvature, determines the all the other curvature tensors. Now let us consider n equals 3. So in this case if you compute D of Rm, so that is going to be 3 squared multiplied by 3 squared minus 1 divided by 12. So that is 72 divided by 12, which is 6. Also for the Ricci tensor you compute this is just 3 times 4 divided by 2, which is 6. So both the curvature tensor and the Ricci tensor have 6 independent components. So it is not surprising that in this case the Ricci basically completely determines the sectional curvature and the curvature tensor. So in fact so of course that is not obvious from the dimension count, but one can check the following. So let lambda 1, lambda 2, lambda 3 be eigenvalues for the Ricci tensor at some point p. It always, I mean the matrix corresponding to the Ricci tensor is symmetric, and so there will be 3 eigenvalues that it will have, 3 real eigenvalues, and let E1, E2, E3 be the corresponding orthonormal basis of eigenvectors. Then in fact if pi ij is the plane spanned by Ei and Ej, then you can completely determine the sectional curvature of this plane in terms of the eigenvalues. So Kij is simply going to be so in a cyclical fashion. So K12 is going to be half lambda 1 plus lambda 2 minus lambda 3. Similarly, K23 is going to be half lambda 2 plus lambda 3 minus lambda 1, and similarly for K13 that is going to be half lambda 1 plus lambda 2 lambda 3 minus lambda 2. Okay. On the other hand, for n bigger than or equal to 4, this actually contains strictly more information than the Ricci tensor. Okay, so in lower dimensions it is actually easier to work and it is completely fine to work with these simpler curvature objects, namely the Ricci tensor in dimension 3 and the scalar curvature or the Gauss curvature in dimension 2. On the other hand, in higher dimensions, in order to completely understand a manifold geometrically, one has to take the full curvature tensor into account. Alright, so that is it for this lecture. For the next couple of lectures, I will talk about the geometry of submanifolds embedded inside the Euclidean space, because many of our examples come from this class of manifolds, and then we learn how to calculate curvature of such manifolds. Okay, so that is the topic for the next couple of lectures. Okay, so that is it for this lecture. Thank you for your attention, and I will see you next time around.